Combinatorics PYQ session. What is the reason behind this PYQ session? Basically, because most of us has completed the PYQ. There are some people who haven't completed the PYQ. That is the first reason. And the second reason is that the combinatorics for PRMO is a small topic, because what's there in the syllabus? Some basic concepts of permutation and combination, I can say. If you want to look at the subtopics, we have permutation, combination with repetition, etc., etc. One or two rare questions from circular permutation, and we have derangements, and then we have derangements, and what else? Some questions with basic of set theory, rarely one or two questions from inclusion exclusion principle, and then if you want, we can give it a special name as Bayes' theorem. And this syllabus is totally unofficial. Based on past year questions, analysis, but the questions that are asked from these topics are really nice and interesting, are good questions. We need to go for case study analysis like this. Before starting this PYQ session, my most favorite problem solving strategy for simple questions on permutation and combination is first combine and then multiply with the arrangements. This is my most favorite problem solving strategy. Another one is that first go for the combinations, not combine, first combinations. Like we have the formula of permutation, right? This NPR formula, very widely used formula, but I never use this formula, because in certain cases, if there are some restrictions in the number of arrangements, then it will be totally messed up. That's why I'm basically using the formula of NCR. I will use first, and then whatever are the possible arrangements, I will multiply them. This is my strategy. Quite easy strategies. Problems are easy. So let's start. This is the most important thing. Let's start with the first question. It's visible, right? There are n-1 red balls, n green balls, n+1 blue balls in a bag. The number of ways of choosing two balls from the bag that have different color is 299. If you're attentive enough, then you might have noticed this statement, which usually appears in most of my videos. And probably this is my favorite success mantra, you can say. And that's even the benefit of recorded lectures. You can take your time. Everything is having an advantage and a disadvantage, and that's the advantage of So let's not waste time. Whenever I will read a question, immediately I will solve that. In between you can pause this. There are n minus 1 red balls, n plus 1 blue balls in a bag. Okay. So we have n minus 1 we have red balls, blue balls, green balls. The number of ways of choosing two balls from the bag that have different color is 299. Okay. Different colors, that means we need to choose any two colors, say red blue, or we can choose blue green or green red. These are the cases we are having with us. Now it's not given that the balls are identical, their color is same. Balls may or may not be identical. So these are the three cases. Now how do we confirm that there are only three cases? Simple, 3 choose 2, because we can choose only two colors, right? It's 3. So there are three cases. The first thing we have confirmed. What is happening? I just wanted to rub it, and what the rubbish happened. Okay, no issues, no worries. I'll write it again. No worries. So there are three cases. 3 choose 2. Three cases. The cases are red blue, blue green, green red. Now red blue, how many possibilities are there? N minus 1, choose 1 into blue, red, n plus 1 blue balls, n plus 1, choose 1. Let us add them. N plus 1 blue balls, n green balls. Then we have the case for green red. How many greens? N green balls multiplied by n minus 1 red balls. We'll get an expression over n, quadratic equation over n minus 1, n plus 1 plus n plus 1 into n into n minus 1. Total number of cases are 299. Simply we will solve this quadratic equation and find out the value of n. And this is your part. This is not my part. This is not my task. Next question. There are 3 kinds of fruits in the market. How many possible ways are there to purchase 25 fruits from them if each kind has at least 25 of its fruit available? We have solved more tougher questions basically when we have seen the lectures of Beggars method. We have solved quite tougher questions as compared to this kind of questions. We have used the so-called binomial theorem, I guess. Yeah, we have used binomial theorem for, even for negative terms, and have applied in this Beggars method. We know how to apply Beggars method in case of restrictions. Say for example, there were cases like a plus b plus c equals to 25. Here it's given that A, B, C. 25 of its kinds are available. A, B, C max. That is A equals to B equals to C equals to 25. 25 are available, but we have solved for cases like B. Okay, just solve this. How many positive integral solutions are there for B, A, comma B belongs to natural number? Find number of find number of uh, triplets satisfying these conditions. Okay, this is a homework. Now let's solve the question that was asked in this PRM examination. There are three kinds of fruits in the market. How many possible ways are there to purchase 25 fruits from among them if each kind has at least 25 of its fruits available? Quite easy, not a great deal. Let the fruits be A, B and C. I want to buy maximum of 25 fruits. Now apply the Baker's formula here. 25 plus 3 minus 1. Choose 3 minus 1. 28, 27. 27. Choose 2. 27 into 26. 2 factorial. 13. 27 into 13. This calculation is your part. 27 into 13. It's not B, it's 13. The old questions are easy, but basically from 2019 onwards, the difficulty level of PRMO has increased. And 2018 also some questions were good, but 2019 onwards difficulty level has increased. Find the number of ordered triplet of positive integer. That I guess already solved in the class. Still, these are PYQs, most of these are solved. Find the number of ordered triplets of positive integers such that ABC equals to 108. This is quite an easy question. Not worse, this is an easy question. Say ABC. Okay, just let me zoom in. That will be better. ABC equals to 108. Let's factorize 108. This is divisible by 4, right? 4 into 27. Oh, nice. 2 square into 3 cube. So ABC are of the format. Since ABC are integers, just look at the questions. ABC are integers. Easy one. I won't take much space even to solve this problem. So A, let us assume that A is of the format A equals to some 2 to the power k1. Okay, not k. Let me give p1. 2 to the power p1 into 3 to the power q1. B equals to some 2 to the power p2 into 3 to the power q2. C equals to some 2 to the power p3 into 3 to the power q3. Apply the most this P1 plus P2 plus P3 equals to 2. This is a basic rule of indices. I guess you all are aware of this. Q1 plus Q2 plus Q3 equals to, see, this is 3, 3. Fine. Now find out the number of cases possible for this. P1 plus P2 plus P3 equals to 2. Find out the number of cases. There are, just look at the formula if you've forgotten the formula. Let me write it. The next session I will give you a brush up for the formulas. Just if you've forgotten. 25 plus 3 minus 1. So say A1 plus A2 plus A3, for those who have forgotten the formula. An equals to some n, right? So this is small n, remember. The number of different kinds of solution set will be n plus n minus 1. Just wait a minute, my stylus is not working. Just wait. N, what happened? Minus 1. Choose n minus 1. I guess I'm correct. Yes, I'm correct. So this is the formula for number of solution set. If you have forgotten the formula, recapitulation is extremely necessary part. So for there, the number of solutions pairs will be 2 plus 3, 4 choose 3 minus 1, 2, and here it will be 5 choose 2. So this is the number of solution pair for P1, P2, P3, and this is for Q1, Q2, Q3. Right, let me separate them. And these all are what? Dependent on each other, right? This Q1, Q2, P1, P2 dependent on each other. So we will simply, to find out the total number of cases, we will simply multiply this quantity with this quantity. So the solution set will be 4 choose 2, 5 choose 2. This was quite easy question. Okay, this is a very good question. There are, okay, let me zoom in the question. Perfect. What's happening today? There are 5 cities. Read the question very properly, because I know that you are going to make the mistake if you haven't seen the lecture. Because in the lecture this question was definitely solved. There are 5 cities A, B, C, D, E on a certain island. There are 5 cities A, B, C, D, E on a certain island. Each city is connected to every other city by road. Each city is connected to every other city by road. Very nice. In how many ways can a person starting from city A come back to A after visiting some cities without visiting a city more than once? Just give stress on this part. Without visiting a city more than once. It's not visible, right? What's happening? What is the perfect color for highlighting? Without visiting a city more than once. And without taking the same road, okay, more than once. The order in which he visits the city also matters. Order matters, it is given. So that means what? From the question only, just reading this sentence, one can have the idea that first we need to make some combination and then we need to arrange them, right? And that was the problem solving strategy I said at the very beginning of the lecture. But one important point that is given here, without taking the same road, more than once. That's an important point. Without taking the same roads. That's easy. So I would say that how many cities are there basically? A, B, C, D, E. B, C, D, E. Other than A, how many cities are there? 4 cities are there. So let me go for this case only. They have given this case. So I'll go for this case. Here he is visiting how many cities? 2 cities out of 4 cities. So this he can do in 4 choose 2 ways, right? 4 choose 2 ways. Am I correct? This you can do in 4 choose 2 ways. Now the arrangement of the city also matters, like BC and CB also matters. So now comes the arrangement. 2 factorial. So this was for when he is visiting 2 cities. This was the case for when he is visiting 2 cities. Now there will be case when he is visiting 3 cities. 4 choose 3 into 3 factorial plus the last case when he is visiting all the 4 cities into 4 factorial. Now some would say that there should be a case that when he is visiting 1 cities, 4 choose 1 into 1 factorial. Those who will do this, they are absolutely wrong. Now why? Why they are wrong? Just if you're doing the sum for the first time, just write this in your copy and cut it down so that you would remember the next time when you saw this. Because, yeah, that was a mistake I did. Now why this is wrong? Let us see. Let us take a case of that a person starts from A, visits a city D, come back to A. From here to here, he is taking the road. Say each city is connected by each other city by only one road, right? It is given in the question. Each city is connected to every other city by road. Only one that we need to consider, because nothing is given, that means only one city is there, one road is there. So from A to D is going with the one road, one particular road. Say the name of road is National Highway NH1. Now again, when he is returning to road A, which road he needs to take? The same road only, NH01. But what is given in the question? What is given in the question? Without visiting a city more than once and without taking the same road more than once. So that's why visiting one cities, it is not possible. This case is wrong. What happens in the case of two cities? Just look at this carefully. The sum is done. I'm just giving you the visualization. Here in this case, say A to C is connected by National Highway 02. C to B is connected by NH03 and B to A is connected by National Highway 04. He's taking NH02 once, NH03 once, NH04 once. So he's not taking a road more than once. And for any other case, for in between, if you're taking the case of three cities also, then also this is valid. But in case of one cities, this is not valid. That we need to carefully solve whenever we are solving the problems. Teacup problem, one of my favorite one. Just this problem is also very difficult problem, I'd say. There are several teacups in the kitchen, some with handles and other without handles. Nice. The number of ways of selecting two cups without a handle. Okay. So, number of cups is unknown. The number of ways of selecting two cups without a handle and 3 without a handle and 3 with a handle is exactly 1200. What is the number of possible maximum number of possible cups in the kitchen? Okay, fine. Number of cups are integral. I hope that I didn't need to elaborate. And we have been asked to find the maximum number of cups. Okay, fine. So first is without a handle. Let the number of cups without a handle be x and number of cups with a handle be y. Number of cup without a handle be x and number of cup with a handle be y. Without handle x, with handle y. First case. Next session I hope will solve from other Olympiads. There are several teacups in the kitchen, some with handle and other without handles. The number of ways of selecting two cups without. So now it's easy. There's nothing difficult. X choose 2 into y choose 3 equals to 1200. Pretty simple. Just factorize 1200. This is 12 into 100. We have 2 to the power 4 into 3 into 5 square. And this will be x into x minus 1 over 2 into y minus 1 into y minus 2 over 6 equals to 2 to the power 4 into 3 into 5 square. Two to the power 5, just multiplying them. 2 to the power 6, right? 2 to the power 6, 3 square into 5 square. So now that is the difficult thing, to find the integral pairs, but it's not impossible one, because we have a lot of time in this kind of examinations like Prmo, so we can spend our time. Let's find out some pairs such that x and y are maximum. Let me start with 6. Suppose y is 6, this is 5, this is 4 then. So 2 cube, 5, 3 is gone. So we are left with 2 cube, 5. How 5 is squared? 5 is not squared. Oh, it's given 5 is squared. Yeah, yeah. 5 is squared. We are left with 2 into 5, and 3 is also gone into 3. This in the form of x into x minus 1. So x into x minus 1, difficult one, right? This is 8, 4 3 ja 10, 11 not possible, 15, 16 not possible. So y equals to 6 is not possible. Let us go for a different case. Say y equals to 5. Y equals to 5. This is 2 square. This is y minus 3. Y minus 2. Sorry. Y minus 2. This would be 3. What are the terms cancelled out? We're left with 5, 3, 2 to the power 4. This in this x minus 1 format. Let's try. This is 15 and this is 16. 16 into 15, clearly visible, right? So one successful case we got. X equals to 5, x equals to 16, y equals to 5. I guess 3 cases are there, as much as I remember. 3 cases are there. This was one case. Let's go for another one. Y equals to 4. Y equals to 4. This is 4, 4. 4. This is y minus 1. 3. Y minus 2. This is 2. So we're left with 2 cube, 3 into 25. This is 24 and this is 25. So x equals to 25, y equals to 4. That's even the answering pair, as much as I remember. Let's try to find out another pair. 6, 8, 7 not possible. 9, 8, 7 not possible. 10, 8, 9, yeah, seems possible. Let this be 10. Zoom in, zoom in, zoom in. This be 10. This be 9. This be 8. 2 to the power 4. 3 square. And 5 gone. We're left with what? We're left with 2 squares. 3 to the power 0. 5. That is 4 into 5. Oh, nice. We got another case. We got another case. X equals to 5. Y equals to 4. So here x plus y is 29. Here it's 15. And here it's 21. So maximum value of x plus y, there is a maximum number of cups in the kitchen is 29. See, if you remember the classical definition of derangement in many books, the classical definition of derangement is given with the help of this postman only. I do not know why. The classical definition of this derangement is given by this postman. So postman has to deliver 5 letters to 5 different, it's not visible. A postman has to deliver 5 letters to 5 different houses. Mischievously, he posts 1 letter through each door without looking to see if its correct address. In how many different ways could he do this so that exactly 2 of the 5 houses receive the correct letter? So this is a classical question from derangement and even an easy question also. There's nothing difficult in the question. Exactly 2 of the 5 houses receive the correct letter. So let me select those 2 houses, 2 lucky houses out of the 5 houses. 5 choose 2. And there are 3 houses left who will not receive the correct letter. Letterbox and letter. There is a definition of derangement. So this is the symbol of derangement. This is called subfactorial. Subfactorial. Derangement of 3. This is a very common figure. So this is our answer. Calculation is not my task. I'm again and again repeating this. Calculation is not my task. And that's even easy calculation. That is 10 and that is 2. So answer will be 20. At a party, each man danced with exactly 4 women, and each woman danced with exactly 3 men. 9 men attended the party. How many women attended the party? Let's assume total number of dance performances be n. Let us assume total number of dance performance be n. So at the party, each man danced with exactly 4 women, and each woman danced with exactly 3 men. 9 men attended the party. How many dances were there? So total number of dances for how many? At a party, each man danced with exactly 4 women, and how many mans were there? There were 9 men attended the party. So this is 9 into 4. Total number of dances, that is 36. Total number of dance performance, let the number of women be W. Let the number of women be W. The question is not visible. Yeah, it often happens. Just a minute. Fine. Now it's visible. At a party, each man danced with exactly 4 men, and each woman danced with exactly 3 men. 9 men attended the party. How many women attended the party? Now it's visible. So total number of dance performance, as we did, 9 men were there, and 4 dance performance by each man. So this is 36. Let the number of women be W. Then we have 3 into W equals to 36, because each woman performed 3 dance performances. So number of women were simply 12. W equals to 12. Less than one line question. These were old Prmo. At that time, there wasn't that awareness. What is the number of ways in which one can? What is the number of ways in which one can choose 60 unit square? This question also, I guess, I did in some class. I didn't remember in which class. What is the number of ways in which one can choose 60 unit square from 11 into 11 chessboard, such that no two chosen square have a side in common? Basically, there are two methods for this problem. First, you draw a small chessboard and analyze the situation. If you can get some hint from a small chessboard even, then one thing you can do, if you have a strong analyzing power. See, I'm drawing a chessboard for you. Let me draw a chessboard. That would be better thing. Looks very. These are the black squares. What is the number of ways in which one can choose? What is the number of ways in which one can choose 60 unit square from 11 into 11 chessboard such that no two chosen square have a side in common? Fine, easy. No two chosen square have a side in common. So we can see in this 3 into 3 chess, we can see in this so we can see in this 3 into 3 chessboard that in how many ways we can select. We can select either the white squares or the black squares. So number of black squares are 1, 2, 3, like this. This is 3 plus 1 from this side. I'm just giving you the hint of the problem. And in this side also this is 3 plus 1. Now let's draw a bigger chessboard. Greater clarification of the problem. We got the hint, right? We got the hint that we need to select this adjacent sides, this side, this side, this side, this side, so that they do not have any sides in common. So we can select either the black or the white, because the white sides are also not having any sides in common. So now let's draw the ideal scenario. Let's draw the ideal scenario. I hope I have already arranged the picture from somewhere. Oh, oh my god. The picture is not there, means I'm in danger. These are the black squares. So how we are going to solve this problem without drawing a 11 into 11 square is that very simple. Diagonally, how many squares will be there? This is a 4 into 4 chessboard. So how many black unit squares will be there? 4, right? Diagonally, there will be 4. Diagonally, there will be 4. Am I correct? I'm correct. In case of 3, we have seen that 3 plus 1. And in case of 4, we're seeing that 4 plus 2. That I'm speaking about this side and then this side. So how many number of squares are decreasing? The first question. 2 number of squares are decreasing every time. So for a 11 into 11 chessboard, this diagonally, how many squares will be there? 11. And then this part, how many squares will be there? 9. Then 7. So on up to 1. Now you just see simply that this side and this side are symmetrical. So we are calculating for one side, but that would be symmetrical. So we need to multiply this by 2 for a 11 into 11 chessboard without drawing the actual 11 into 11 chessboard. That's the number of black squares in a 11 into 11 chessboard. 11 plus 2 into n into n plus 1, 2 plus 1, 2 into, right, 10 by 2. This is the sum of first n terms formula, n into n plus 1 by 2 multiplied by 2. This 2 shifted to this 2. So these and these are cancelled. We have 90. Pretty varied kind of results I'm getting. 90 plus 11. 101 black squares. That's not possible, right? Because in a 11 into 11 chessboard, the total number of black squares are total number of squares are 121. So how there can be 101 black squares? This is not possible. Varied. Okay. This is not possible. One way to solve the problem, because I'm having some difficulty in visualizing the problem, that let's draw 11 into 11 square. And another way I would say that what are the total number of squares? 121. This is a 3 into 3 square. So here how many unit squares are there? 9. 3 into 3, 9. So among them 5 are red and 4 are white. 4 are white. Here also we can see 1, 2, 3, 4, 5, 6, 7, 8. 8 are black 8 are white. So when the total number of squares are odd, that is a 3 into 3, 5 into 5, 5. At that case, it's clearly visible that, say, either the number of black squares will be either the number of black squares will be 61 black, 60 white, because the sum is odd, or there is a possible that 60 black, 60 white, 61 white, 61 white. So these are the two possibilities. So the color of the squares doesn't matter, right? So let us assume the second case. So we need to select 60 squares. Out of them, total number of possibilities will be 60, choose 60. We can select either the black squares who are adjacent to each other or the white squares. I'm using the word or, that's why we are getting plus. 61, choose 1, and this adds up to 61. So now I guess we are not having any kind of difficulty in visualization, because the total number of squares are what? 11 into 11, that is 121, which is an odd number. So either 60 plus 61, 121, or 61 plus 60 equals to 121. These are the two possibilities we are having. So this was quite easy problem. I just created the mess with the problem. Now these last two problems are one of the most beautiful and difficult questions based on the previous analysis. What is the number of ways in which one can color? What is the number of ways in which one can color the squares of a 4 into 4 chessboard with colors red and blue, such that each row as well as each column has exactly 2 red squares and blue squares? It's a beautiful question from Prmo 2018. So this is a 4 into 4 chessboard. We want to color it with colors red and blue. With colors red and blue. In how many ways we can do so? This is also easy question. Say this is blue. Say this is blue, this is blue. So for the blue colors, how many positions we can select? In how many different ways? 4, choose 2. That is 6 ways are there. And for the next row, similarly we have 4, choose 2 options. That is 6. 6 times 6 is 36. So for arranging the first two rows, we have 36 options. Now we will divide this 36 into 3 different cases to get out our answer for the next two rows. We will divide this 36 cases upon sub cases so as to get the suitable cases for row 3 and row 4. Let's erase them. Total for the first two rows we have 36. Now we will take the case when row 1 and row 2 are exactly the same, row 1 not equals to row 2, and exactly 2 element. The third case will be exactly 2 element matches. We'll explain the case. No worries. Let's go for this first case. Row 1 and row 2 are same. This is the first case. Row 1 and row 2 are same. Say here is blue. here is blue, here is also blue. So row 1 and row 2 are same, here will be blue, here will be blue. This can be arranged in 6 ways. 4 choose to 6 ways. This can arranged in only one ways. Now comes row 3 and row 4. In how many different ways we can arrange them? Just take for the case of simplicity that if this is blue blue, then this has to be red red. Quite simple. And this has to be red red. Because every row as well as every column has 2 red as well as 2 blue. That case we need to satisfy. So for here also we are having only one possibilities of arranging, one possibilities of arranging. Total number of ways are nothing else but 6 for this case when row 1 and row 2 are same. Now let's go for the case when row 1 not equals to row 2. Row 1 not equals to row 2. Suppose here we are giving it red color, here we are giving it red color, here blue, here blue. Now they are not equals. Means what? Unique case, blue, red, blue, red. This is the case when row 1 and row 2 are not equal. Now this can be arranged in 4 choose 2 ways, that is 6 ways. This is only having one way. Similarly, this row can again be arranged in 6 ways and this can be arranged in 1 ways. Total cases here is 36. So let's zoom in. Now the case when exactly 2 element matches. We have seen the case when every element matches. We have seen the case when no element matches. Now the case when 2 element matches will be what? 36 was the total number of arrangements. Minus 6, minus 6. 36 was the total number of arrangement for the first 2 cases. We are subtracting the other 2 cases. We'll get the last case when exactly 2 element of row 1 and row 2 matches as 24. Here we are having 24 options. We need to find the options for here. We'll get the total number of options. This we can do in other methods also, but that's we are doing this. The basic addition and subtraction principles. Here is red. So here is red. Here is red. Exactly 2 matches. Here is blue. Here is blue. So exactly 2 matches. Red, this is matching. This is not matching. One blue is matching. One blue is not matching. This is one possibility. Just look at this very carefully. Another possibility is also there. Another possibility that this can be blue. This can be blue. Say this is blue. This is blue. This is red. This is red. This is another possibility. So for this row, we are having 2 possible cases. 2 possible cases. Okay. So in this way, we can find out that when exactly 2 element matches, that the total number of ways are 24. But we have already did this using this subtraction principle. So we do not need to bother for that. Now this is one case when exactly 2 element matches. We need to find out the cases for this row 3 and row 4. So 2 red, 1 blue. 2 red, 1 blue. This has to be blue also. This has to be blue. because every column is having 2 blues and 2 reds, and 2 blue, 2 red. This is fixed, kind of fixed. But what we can have multiple arrangement is this region, is this region, is this region. Here we will get multiple arrangement. How? Let's see. Here 1 is blue, we can give it blue, we can give it blue, we can give it red, we can give it blue, we can give it red. One such possibility. Another such possibility, I am showing it over here. Another such possibility, and it's satisfying, that this is blue, this is red, this is blue, this is red. This is also satisfying. So here we are getting 2 cases for these 2 rows. 2 cases, right? We will simply multiply this 24 into 2 and we get the total number of cases as 48 for the last case when exactly 2 element matches. 48 plus 36 plus 6. So total is 48 plus 36 plus 6. This is our answer. This is one of the most beautiful question asked in the history, I would say. And such kind of question with derangement over rows and column was asked probably in, just look at the question paper, AMC 2020 or AMC 2021. Okay, just look at the question paper, you'd get it. So this was asked in Ioqm. 3 couples sit for a photograph in 2 rows of 3 people each, such that no couple is sitting in the same row next to each other or in the same column one behind the other. How many arrangements are possible? Fine, easy only. That's easy, not difficult. There are 2 solutions proposed for this problem by most of the people. So one solution is based on this case based solution, and that is a more appropriate solution according to me, more logical and easy to visualize also. The scenario is quite easy. Last few questions were based on these rows and columns, even in the past few years, coloring rows, columns. So let me name them as husband 1, husband 2, husband 3. Okay, wife 1, wife 2, wife 3. So the first configuration is that husbands and wives in different rows, say husband 1, husband 2, husband 3. Now they can be arranged in the first rows in 3 factorial ways. Below them we cannot have wife 1, wife 2, wife 3, right? So this is this we cannot have. So this is the simple case of derangement. Consider the husbands as letter boxes and the wives as letters. So we got the case of derangements. So this is derangement of what? Subfactorial 3. This is you calculate that, right? I'm not calculating. This is 6 as much as I know, and this is 2. That formula is there na? Derangement of 3 is 3 factorial 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial. That formula you can use, right? I'm showing you. No issues, no worries. 113 factorial. Easy to achieve. Easy. 6 over this cancelled out. 2, this is 3 minus 1 over 6 cancel. So, clear. Subfactorial 3 equals to 2. There's a formula, you can just go for the get the formula there. So now this was one case when husband was in the upper row. There is a possibility that the wives are in the upper row. So there are two possibilities. So the total number of possibility are 2 into 6 into 2, or more appropriately I would say 2 into 3 factorial into subfactorial of 3, more appropriate. This is more appropriate. This is the resultant, which is equals to 24. When husbands and wives are in the same rows and same columns, are not in the same rows and same columns. So the next case, say 2 husband, 1 wife. This is the case. 2 husband, 1 wife. Say H1, H2, W3. They can be arranged in three factorial ways. Similarly, derangement of 3 factorial. Now this H1, H2, H3, W3, they can be selected in how many ways? First, 2 husband we are selecting out of 3. That is 3 choose 2, and we are left with just a minute. If it's 3 choose 2, then it would be pretty large enough. Oh yeah. In our selection, you just see for H1, H2, we are freely arranging them. We cannot select W1 or W2. We need to obviously select W3. So for the wives, there will be only one case. This multiplied to 3. Understand? We cannot select this. We cannot select them. The case with 2. Okay. I hope it's clear now. So number of choices are, I'm just writing down the case for more clarity. H1, H2, W3, H2, H3, W1, H3, H1, W2. These are the 3 cases, right? These 3 cases we got, and it's a possibility that another possibility like W1, W2, H3. For that, we will multiply the whole expression by 2. So here the total number of possibilities we are getting 3 into 2 into this 24. That is, oh, sorry, 3 into 24. Simply 3 into 24. Other cases are same, right? This is 72. So total number of cases are 72 plus 24, 96. Done.